In the study of past climates, climate proxies are preserved physical characteristics of the past that stand in for direct meteorological measurements and enable scientists to reconstruct the climatic conditions over a longer fraction of the Earth's history. Reliable global records of climate only began in the 1880s, and proxies provide the only means for scientists to determine climatic patterns before record keeping began. Examples of proxies include ice cores, tree rings, subfossil pollen, boreholes, corals, lake and ocean sediments, and carbonate speleothems. The character of deposition, a rate of growth of the proxies material, has been influenced by the climatic conditions of the time in which they were laid down or grew. Chemical traces produced by climatic changes, such as quantities of particular isotopes, can be recovered from proxies. Some proxies, such as gas bubbles trapped in ice, enable traces of the ancient atmosphere to be recovered and measured directly to provide a history of fluctuations in the composition of the Earth's atmosphere, to produce the most precise results. Systematic cross-verification between proxy indicators is necessary for accuracy in readings and record-keeping. Proxies can be combined to produce temperature reconstructions longer than the instrumental temperature record and can inform discussions of global warming. The distribution of proxy records, just like the instrumental record, is not at all uniform, with more records in the northern hemisphere. Proxies. In science, it is sometimes necessary to study a variable which cannot be measured directly. This can be done by proxy methods, in which a variable which correlates with the variable of interest is measured, and then used to infer the value of the variable of interest. Proxy methods are of particular use in the study of the past climate, beyond times when direct measurements of temperatures are available. Most proxy records have to be calibrated against independent temperature measurements or against a directly calibrated proxy during the period of overlap to estimate the relationship between temperature and the proxy. The longer history of the proxy is then used to reconstruct temperature from earlier periods. Ice cores. Drilling ice cores are cylindrical samples from within ice sheets in the Greenland, Antarctic, and North American regions. First attempts of extraction occurred in 1956 as part of the International Geophysical Year. As original means of extraction, the U.S. Army's Cold Regions Research and Engineering Laboratory used an 80-foot-long modified electro drill in 1968 at Camp Century, Greenland, and Byrd Station, Antarctica. The machinery could drill through 15 to 20 feet of ice in 40 to 50 minutes, from 1,300 to 3,000 feet in depth. Core samples were 4 1/4 inches in diameter and 10 to 20 feet long. Deeper samples of 15 to 20 feet long were not uncommon. Every subsequent drilling team improved the method with each new effort. Proxy presence of water molecule isotopic compositions of 16O and 18O in an ice core helped determine past temperatures and snow accumulations. The heavier isotope condenses more readily as temperatures decrease and falls as precipitation, while the lighter isotope can fall in even colder conditions. The farther north elevated levels of an 18O isotope are detected signals are warming over time. In addition to oxygen isotopes, water contains hydrogen isotopes 1H and 2H, usually referred to as H and D, that are also used for temperature proxies. Normally, ice cores from Greenland are analyzed for delta 18O and those from Antarctica for delta deuterium. Those cores that analyze for both show a lack of agreement. Air bubbles in the ice, which contain trapped greenhouse gases such as carbon dioxide and methane, are also helpful in determining past climate changes. From 1989 to 1992, the European Greenland Ice Core drilling project drilled in central Greenland at coordinates 72 degrees 35 N, 37 degrees 38 W. In the project, ice at a depth of 770 meters were 3,840 years old, 2,521 meters were 40,000 years old, and 3,029 meters at bedrock were 200,000 years old or more. However, ice cores can reveal the climate records for the past 650,000 years. Location maps and a complete list of U.S. ice core drilling sites can be found on the website for the National Ice Core Laboratory, http://nicl, usgs.gov, core site, htm tree rings. Dendroclimatology is the science of determining past climates from trees, primarily from properties of the annual tree rings. Tree rings are wider when conditions favor growth, narrower when times are difficult. Other properties of the annual rings, such as maximum latewood density, have been shown to be better proxies than simple ring width. Using tree rings, scientists have estimated many local climates for hundreds to thousands of years previous. By combining multiple tree ring studies, scientists have estimated past regional and global climates. Fossil leaves. New approaches retrieve data such as CO2 content of past atmospheres from fossil leaf stomata and isotope composition, measuring cellular CO2 concentrations. A 2014 study was able to use the carbon-13 isotope ratios to estimate the CO2 amounts of the past 400 million years. The findings hint at a higher climate sensitivity to CO2 concentrations. Boreholes. Borehole temperatures are used as temperature proxies. Since heat transfer through the ground is slow, temperature measurements at a series of different depths down the borehole, adjusted for the effect of rising heat from inside the Earth, can be inverted to produce a non-unique series of surface temperature values. The solution is non-unique because there are multiple possible surface temperature reconstructions that can produce the same borehole temperature profile. In addition, due to physical limitations, the reconstructions are inevitably smeared and become more smeared further back in time. When reconstructing temperatures around 1500 AD, boreholes have a temporal resolution of a few centuries. At the start of the 20th century, the resolution is a few decades, hence they do not provide a useful check on the instrumental temperature record. However, they are broadly comparable. These confirmations have given paleoclimatologists the confidence that they can measure the temperature of 500 years ago. This is concluded by a depth scale of about 492 feet to measure the temperatures from 100 years ago and 1,640 feet to measure the temperature from 1,000 years ago. Boreholes have a great advantage over many other proxies in that no calibration is required. They are actual temperatures. However, they record surface temperature, not the near-surface temperature used for most surface weather observations. These can differ substantially under extreme conditions or when there is surface snow. In practice, the effect on borehole temperature is believed to be generally small. A second source of error is contamination of the well by groundwater may affect the temperatures, since the water carries more modern temperatures with it. This effect is believed to be generally small, and more applicable at very humid sites. It does not apply in ice cores where the site remains frozen all year. More than 600 boreholes on all continents have been used as proxies for reconstructing surface temperatures. The highest concentration of boreholes exist in North America and Europe. Their depths of drilling typically range from 200 to greater than 1,000 meters into the crust of the Earth or ice sheet. A small number of boreholes have been drilled in the ice sheets. The purity of the ice that permits longer reconstructions. Central Greenland borehole temperatures show a warming over the last 150 years of approximately 1 degree Celsius plus or minus 0.2 degrees Celsius, preceded by a few centuries of cool conditions. Preceding this was a warm period centered around AD 1000, which was warmer than the late 20th century by approximately 1 degree Celsius. A borehole in the Antarctica ice cap shows that the temperature at AD 1 approximately 1 degree Celsius warmer than the late 20th century. Borehole temperatures in Greenland were responsible for an important revision to the isotopic temperature reconstruction, revealing that the former assumption that spatial slope equals temporal slope was incorrect. Corals. Ocean coral skeletal rings, or bands, also share paleoclimatological information, similarly to tree rings. In 2002, a report was published on the findings of Drs. Lisa Greer and Peter Swart, associates of University of Miami at the time, in regard to stable oxygen isotopes in the calcium carbonate of coral. Cooler temperatures tend to cause coral to use heavier isotopes in its structure, while warmer temperatures result in more normal oxygen isotopes being built into the coral structure. Denser water salinity also tends to contain the heavier isotope. Greer's coral sample from the Atlantic Ocean was taken in 1994 and dated back to 1935. Greer recalls her conclusions. When we look at the averaged annual data from 1935 to about 1994, we see it has the shape of a sine wave. It is periodic and has a significant pattern of oxygen isotope composition that has a peak at about every 12 to 15 years. Surface water temperatures have coincided by also peaking every 12.5 years. However, since recording this temperature has only been practiced for the last 50 years, correlation between recorded water temperature and coral structure can only be drawn so far back. Pollen grains. Pollen can be found in sediments. Plants produce pollen in large quantities and it is extremely resistant to decay. It is possible to identify a plant species from its pollen grain. The identified plant community of the area at the relative time from that sediment layer will provide information about the climatic condition. The abundance of pollen of a given vegetation period a year depends partly on the weather conditions of the previous months. Hence, pollen density provides information on short-term climatic conditions. The study of prehistoric pollen is palynology. Lake and ocean sediments. Similar to the study on other proxies, paleoclimatologists examine oxygen isotopes in the contents of ocean sediments. Likewise, they measure the layers of valve laminating lake sediments. Lake valves are primarily influenced by summer temperature, which shows the energy available to melt seasonal snow and ice, winter snowfall, which determines the level of disturbance to sediments when melting occurs, rainfall, pseudo proxies, the skill of algorithms used to combine proxy records into an overall hemispheric temperature reconstruction may be tested using a technique known as pseudo proxies. In this method, output from a climate model is sampled at locations corresponding to the known proxy network, and the temperature record produced is compared to the overall temperature of the model.